Greetings to my Calculus 3 course. This will be the first part of our 25th lecture, and this is a lecture associated with April 7th, Tuesday of the spring term of 2020. Sorry, I forgot to put the date on the lecture notes here. You will also note that I did manage to get rid of the lines, the horizontal lines across our scanned notes, so that's excellent. The first part of today's lecture, part 1 here, is going to deal with the final point I want to make on double integrals. We have seen that double integrals can be used to find certain volumes. In particular, if you want to find the volume between a region of the plane and a surface which remains non-negative across that region, you can integrate the equation which gives you the surface over the region to find the volume between those two surfaces, one being a subset of R2, the xy plane, and the other being the surface given by your equation. So that's a way to find certain volumes as double integrals. You can also, in some sense more naturally, use double integrals to find areas, and that's what we're going to discuss in the first part of today's lecture. So we'll begin with the theorem, area via double integrals. If R is a region of the plane, then the area of R, which we could designate as capital A of R, meaning the area of R, is given by the double integral of the constant integrand 1 taken across the region R. So to find the area of a region using double integrals, you integrate across that region and you take your integrand to be the constant function 1. If you remember, if you think of 1 as z equal to 1, this is just a horizontal plane at height 1 above the xy plane. So that is your integrand. And the region that you take this double integral over is the region that you're interested in the area of. So the intuition as to why this theorem works, if you have your region R in the plane here, and you take a constant function 1 across that region, this is just a height 1 above. The previous theorem that we had for calculating volume says that the volume of this region is going to be given by the integral of 1 over that region. So the volume of this three-dimensional region is given by the double integral that we are discussing, but the volume of this region is also equal to just the area of R numerically. The units would be different. If we were working in meters, the volume would have meters cubed as a unit, and the area would have meters squared as a unit. But because the height is everywhere 1, it's actually the numerical value for the volume is equal to the area for the region R. And it's because you have height 1. If R was, say, a circle and it had area equal to 6 meters squared, and then I take this volume by creating a surface that has height 1 at every point above that circle, then if I were to find the volume of that region, I would take the area of the base, which was 6, we said, meters squared, and multiply it by the height of the object, which has value 1 meter, and that would give me 6 meters cubed for the volume. So that numerical value of 6 meters cubed in the meters cubed expression is equal to the numerical value of 6 for the volume in terms of meters squared there. I'm sorry, 6 for the area. So the volume of the whole region would be the area of the base times the height. That would be 6 meters squared times 1 meter, giving me 6 meters cubed. That numerical value of 6 associated with that volume is the same as the numerical value 6 associated with the area of the base. And it's because you're taking area of the base times height, and the height is everywhere 1 here. So our previous theorem told us that the volume of this region would be the double integral of 1 across the region, 1 being the upper surface here, and now we know that that's also equal to the area of the region itself. So we can use these double integrals to find the areas of regions of the plane just by taking our integrand to be the constant function 1. We're about to start talking about triple integrals in today's lecture, and there will be a similar theorem that says if you want to find the volume of a region of R3, you can just integrate the constant function 1 across that region of R3. That'll be a triple integral of 1 across a region of R3. Here we're taking a double integral of 1 across a region of R2. So let's think about an example and a sample problem. We'll see more problems of this type in the homework, but we're going to wrap this topic up fairly quickly with one example and one sample problem. There's no new computations in what we're doing. There is only a new interpretation. This idea that you can find area by setting your integrand to be 1. So let's derive the formula for the area of a disk. You might also say the area enclosed by a circle. We generally think of this formula as the area for a circle formula. It's the famous pi r squared that we're going to derive here. But we will, in the language of this course, state it a bit more carefully and say let's find the area of a disk with radius r0. And I'm letting the radius here be r0 just so it looks different from our variable r in polar coordinates. So they didn't tell us anything about where the disk is centered. All disks of this radius are going to have the same area regardless of where their center happens to lie. And so we're free to choose the position of the center, and we'll take it to be the origin because that's going to make the disk easily expressible in terms of polar coordinates. If I take the disk to have radius r0 and have center at the origin, I could draw it thusly. We're going to call it r. We might call it D for disk if we wanted to be clever here, but we're not, or I'm not. And to express this disk in polar coordinates, we will let theta go from 0 to 2 pi because this region has full circular symmetry. Every value of theta between 0 and 2 pi is associated with some region of this disk. And we'll be letting r, our variable, go from 0 up to r0. So that is the expression of a disk of this type in polar coordinates, where the radius is arbitrary but a fixed constant. And now our theorem tells us that the area of this region will be the double integral of 1 over the region with respect to area. This first equality is the payload of the theorem. Now I can compute this double integral any way that I like. In particular, I could compute it in Cartesian, I could compute it in polar. If I'm working in Cartesian, it might just be a Cartesian rectangle, or it might be a more general region that I would prefer to express as type 1 or type 2. So all of the computational theory that we've developed for computing double integrals could come into play at this point. The new information, or the new ideas that we're studying today, are just that area can be computed as a double integral of this type. How you compute that double integral is up to you and could depend upon the circumstance. Here we've already expressed the region in polar, so we're going to compute this double integral in polar coordinates. So my dA expression becomes r dr d theta. I've still got 1 here, and r is going from 0 to r0, and theta is going from 0 to 2 pi, as we decided on the last slide when we thought about expressing this disk in polar. This is an example where all of my limits of integration are constants, despite the fact that r0 is not known. It's still a constant value here. And my integrand factors nicely into a function of just theta. It's the constant function 1, and a function of just r, which is this factor of r that we introduced in our dA expression. So I'm able to factor the double iterative integral into two single integrals. The integral of 1 from 0 to 2 pi is just 2 pi. The integral of r from 0 to r0 is going to be 1/2 r squared, going from 0 to r0. I end up with a 1/2 r0 squared, the 1/2 and the 2 cancel, and I get my pi r0 squared, the famous formula for the area of the circle. We're actually able to calculate that now in this course. It's also one minor point of interest here. We said that this trick for finding area as the integral of 1 over a two-dimensional region is going to generalize to finding volume as a triple integral of 1 over a three-dimensional region. It actually also falls back to the one-dimensional case. Right here, we are finding the length of the interval from 0 to 2 pi, that being 2 pi, as the integral of the constant function 1 with respect to theta as a single integral. So integrating 1 for a single integral gives you the length of the interval that you're integrating across. Integrating 1 for a double integral gives you the area of the region that you're integrating across. And shortly we'll see that integrating the constant function 1 as a triple integral over a region of 3 space will give you the volume of that region of 3 space. So this idea is generalizing nicely as we move up through dimensions here. And I think it's awesome that we can compute. We now have enough mathematical tools and enough mathematical sophistication to actually derive simple geometric formulas of the type that we grew up having to memorize likely in secondary school. So you can now actually prove that the volume, rather the area enclosed by a circle, is given by pi r squared. Sample problem. Let's have you folks do one of these. I want you to find for me the area of the region which is bounded between these two parabolic curves. So y equal to 3x squared and y equal to 2x squared plus 4. Those two curves, if you draw them, you should see that there's a region bounded between them, and I would like for you to find for me the area between these two curves, the area of that region bounded between them. Alright, that is hopefully enough time for you to pause the video and to have some work done on this problem. Let's take a look at a solution. So we are dealing with a Cheshire Cat smile situation yet again here. This is the parabola 3x squared. It touches the origin and it increases a bit more steeply than our other parabola 2x squared plus 4, which has been shifted up 4 units, but does not increase quite so quickly, so that these two parabolas do cross at 2 points. And I am looking at this and seeing that these 2 points where the parabolas cross, I could drop those down to the x-axis, let those be my bounds for my x variable, and then my y variable could move from the lower curve to the upper curve. That's what's given us these lines that look like the divisions between the teeth in the Cheshire Cat smile. But in fact, the idea is that I'm letting A slide from A to B. I'm letting X slide from point A to point B on the x-axis, and then Y will be going from lower curve to upper curve for each such value of X. So to me, this looks like it will be most naturally expressed as a type 1 region. And so the first thing I have to do is find my constant bounds for X. I do that by setting the equations for these two curves to be equal to each other in order to find the points of intersection between them. So 3x squared is set equal to 2x squared plus 4. I subtract over one equation and I end up with x squared minus 4. 3x squared minus 2x squared giving me just x squared minus 4. I then factor that. It is a difference of two squares, so it factors to x minus 2 and x plus 2. You can double check by foiling, see that the inner and the outer products cancel. And this has solutions exactly -2, which will make this factor 0, and 2, which will make this factor 0. The only way to make the product 0 is if one of the factors is 0, and those occur for two specific values of x. So x is going from -2 to 2, that's my a and b, and for each of those x values, y will be going from the lower curve up to the upper curve. And again, graphing it is good, so you can be very sure, just sketching rather, the graphs of these functions is good, so you can get a nice geometric handle on what's going on. It also allows you to determine quite quickly what the lower curve and what the upper curve should be for your y bounds. So now we have this region expressed as a type 1 region. To find the area of the region, we're going to integrate 1 across the region. This first equality, I already knew that that's what I was going to do because I was looking for the area of a region in R2. The work that we did previously was figuring out how best to take this double integral of 1 over R. And because R is readily expressed as a type 1 region, we're going to perform this integral in Cartesian and as an integral over a type 1 region. So my outermost integral needs to have the constant limits of integration. That'll be an integral with respect to x that comes last, going from -2 to 2. My innermost integral has variable bounds which depend on x. Here from 3x squared, the lower curve, up to 2x squared plus 4, the upper curve. We perform the integration. The antiderivative of 1 with respect to y is just y. Here I have my bounds for y. My integral with respect to x is waiting in the wings here. I'm going to plug in the upper limit and then subtract off the value of the antiderivative at the lower limit. I'm going to simplify that expression to get this polynomial of a single variable as my integrand in an integral with respect to a single variable. So at this point it's a simple Calc 2 problem. I take an antiderivative of opposite of x squared and get -1/3 x cubed. I take a derivative of the constant 4 and get 4x. That's going from -2 to 2. I'm plugging in 2 here. 2 cubed is 8, so I get -8 over 3. 4 times 2 is also 8, so I've got a +8 expression here. Minus the same thing at -2, and I'm just getting the opposite of the result I got at 2, since this is in fact an odd polynomial. And so I'm looking at the opposite of -8, which is 8, plus 8 to give me 16, and I've got a -8/3 and a -8/3 to give me -16 over 3. 16 minus 1/3 of 16 is going to give me 2/3 of 16 remaining, and then 16 times 2 is 32, so I'm looking at 32 over 3 as the area of the Cheshire Cat smile in this problem. And this is, again, neat. This is a fairly arbitrary region that we began with. If I just tried to operate using geometry strictly and no calculus, I would be at a loss as to how to find the area of this non-rectangular region. It's not a triangle, it's not a circle, it's not any type of regular geometric region that we have nice formulas for. But using the techniques of multivariate calculus, I'm able to calculate the precise numerical value of the area of this region. So this is expanding our toolkit a bit and the kinds of problems that we can answer here. And that'll do it for our wrap-up for double integrals. This is a topic that we could have discussed earlier. I think I dropped it somewhere along the way. So I definitely wanted to introduce this idea as a nice, if somewhat theoretical, application of these double integrals. And that'll do it for this part of this lecture.